Hello, my name is Mr. Fontenot. Welcome to my YouTube channel, Mr. Fontenot 1111. Please like, share, and subscribe. This video, I'll be calculating the AC values from the Chapter 15 Math handout, problem number 11. Alright, so I've got some lettering here on this circuit, A, B, C, D, E, and F. I want to kind of go over how the current is going to flow through this circuit. When we begin our current, all of our current has to flow from A to B. When we get to point B, the current is going to split. Some of it's going to continue to go up R2. Some of it's going to continue to go to point C through R3 to point D, back around to E. The current that left B headed to E will rejoin that current, and all of the current will go from point E to point F. So from point A to point B is known as our main branch, and from point E to point F is known as our main branch. And this will come in to be very important here in a minute. Since this is a basic combination circuit and not a random unknown, our first step is going to be to find RT. So looking at the circuit here, I see that resistors 2 and 3 are in parallel with each other. If we were to eliminate resistor number 1, if we put a giant wire here that covered up resistor number 1, and we put a giant wire here that covered up the other part of our main branch, we can look at the circuit here and see that it is a parallel circuit. Of course, since R1 is there, it's not parallel, it's combination. But the first step I'm going to take is I'm going to combine the values of R2 and R3. That's going to be the first step that I take in order to find my RT value. So to begin with, I'm just going to bring R1 straight over, leave him 100 ohms, and I'm going to use the reciprocal formula across R2 and R3. So I have 1 over under 150, scroll over, plus 1 over under 200, hit equals, hit engineering, and this gives me 85.71 ohms. That's the equivalent value of R2 and R3. Alright, my second redraw here, I see that I have 100 ohms in series with 85.71 ohms. What do we do with resistors in series? We just add them together. So this shows me that my total resistance will be 185.71 ohms. Anytime I can get 2 out of 3, I can solve for the third. So I see that I do have VT and RT, so I can solve for IT. So IT would be equal to the 10 volts over 185.71, giving me a total current of 53.85. I'm going to round the second number after the decimal place, milliamps. Now this is where the current drawing that I had showed you come in. So as I discussed, the current's going to remain the same from A to B, but once it gets at point B, it can split. Some will go on to C, to D, back around to E, and some will go from B to E. But however many ways it splits, it all has to come back together from E to F. So that tells us that whatever's on the main branch, and the main branch is from A to B and from E to F, whatever's on the main branch, whatever resistors on the main branch, it will get total current flowing through it. So R1 located on the main branch will get the full 53.85 milliamps. That's our second step in solving the problem. IT and I1. Alright, now we've got 2 out of 3 for V1, so 53.85 milliamps times 100 ohms. Gives me 5.39 volts. Okay, now if this was just a parallel circuit and R1 was not here, we know that voltage stays the same in parallel and that we would have the full 10 volts across R2 and R3. R2 and R3 will have the same amount of voltage, but since we dropped 5.39 volts at R1, then the full 10 volts cannot be across R2 and R3. So what we do is we subtract the 5.39 volts from the VT of 10 volts, and that gives us 4.61 volts for both R2 and R3, V2 and V3 values. And that's where this equation comes in. V2 is equal to V3. They will be the same, which will equal VT minus V1. All right, so now we've got 2 out of 3 for I2. We can solve for that. 4.61 divided by 150 ohms gives me 30.73 milliamps. And for I3, it's going to be 4.61 divided by 200, giving me 23.05 milliamps. If I add 30.73 and 23.05, I get the 53.85 milliamps, or thereabouts. There's a little bit of numbers that are not exactly right due to rounding, but close enough. All right, so now that I've taken all of my RMS steps here, found RT, found IT and I1, found V1, V2, V3, I2, and I3. Now I will use my formula sheet, Chapter 15 formula sheet, to find my AC values. So the first thing I'm looking for is V2 peak. Well, I need to understand that all of these current values and all of these voltage values are RMS values. Unless otherwise stated, all values given are in RMS. So when we were given the VT of 10 volts, it didn't say that it was anything other than RMS, so we know that it's RMS. All right, so I need V2 peak. So I'm going to take my V2 of 4.61. I am looking for peak. If I'm looking for peak, it is equal to the RMS value times 1.414. V2 RMS value is 4.61 times 1.414 to give me V2 peak, and it's equal to 6.52 volts. All right, RT, well, resistance is unaffected by whether it's AC or DC or across a resistor, so RT is just RT. So it is 185.71. Now I need I2 peak to peak. So my formula shows me here that in order to get peak to peak, I have to have peak to peak is equal to peak times 2. So the first thing I want to do is find I2 peak. So I take the I2 value of 30.73. Since I know that my answers are going to be in milliamps, I don't have to put the milliamps in here since I know that the answers are going to be in milli. So it's 30.73 times 1.414. That gives me peak. Then when I say times 2, that gives me the peak to peak value, 86.90 milliamps. So basically what we're going to do is we're going to work the problem like you would for DC, giving you all of your RMS values. Then you look for the exact AC value requested and just run the RMS value through the formula to give you the AC value.